And Scott, the mic is yours.
Awesome. Cool. Well, thank you so much, Mike. I really appreciate the opportunity to chat with your team and your audience. So just looking through what we'll cover in the next hour or so, and I know there's always a lot of questions around manufacturing, and it's not typically a very well understood process. So what I'd like to do is shed light on what actually does happen when you've completed the prototype and are thinking about building in higher volume, so that we can understand all the steps to get to that saleable product delivered to your customer. And towards that end, what I'll start with is looking at some of the ways that manufacturing is challenging. Because often if we can understand what's hard, then we can figure out how to put together approaches to set ourselves up for success, which is what I'll do next. I'll touch a little bit on design for manufacturing and assembly. This is a very rich and deep topic, so I won't have much opportunity in this forum to go super deep, but at least I can hopefully build some awareness to it. And then finally, I'll finish up with the thing that kills most hardware companies faster than anything else, which is running out of money. So I'll give you some tools to understand your cash flow so that you can hopefully avoid this. And of course, questions and answers. Feel free to throw something on the chat. And Mike, if you're watching the chat, feel free to jump in anytime, and we'll go from there. So generally, when we think about manufacturing, we need a starting point. And as I look at it, it's typically a works like and looks like prototype. It's frequently useful to split them into two different parts. So the works like has all of the functionality you need. In this slide, I'm using Pebble, which some folks might have seen. It was the first really successful Kickstarter as an example. And in the top left slide there, we've got their actual works like model. So you can see it's got the electronics outside of the watch, and it's leveraging a display to basically provide the core functionality, but it's obviously not packaged, it's not aesthetic, it's not waterproof. Then other part is what we call the looks like, which is the aesthetic model. And the advantage here of separating them into two different models or two different approaches is you don't really need to worry about packaging, but you can work on the engineering on one side and then the aesthetics on the other side, with the goal of ultimately bringing them together and then building it forward. But generally, when you're to this point, it's a good time to start thinking about manufacturing. So a little bit of my background, just so you can understand the lens that I'm looking through. I've had a chance to work on a bunch of really fun robotic projects along the way, from robotic tuna fish in graduate school for the US Navy, where we were trying to find a way to provide more efficient propulsion for autonomous undersea vehicles. And the tuna was kind of the natural fit for that. So we tried to replicate it in the form of a robot. One thing led to another, and in my case, that led me over to Walt Disney Imagineering, where instead of building tuna fish, I got to build full-size walking robotic dinosaurs. So think about a 12,000-pound, 12-foot-long Triceratops powered by a Corvette engine, and you'll get the idea. So that was an insane amount of fun. But those were also all onesies, twosies, where you could, file everything to fit, and really it was fine to work on the robot itself. I guess is more relevant to what I've done for the last 20 plus years is in high volume manufacturing. So I joined iRobot in the early days in the late 90s. And at that point, iRobot was really focusing on robots for the military. So we had different minesweepers with all sorts of cool chains that would light off the mines and other surveillance vehicles. But people kept asking for this robot that would clean their floor. So we thought, all right, we should probably build that, except we have no idea how to manufacture it. So in those days, there weren't great resources like this series that Mike's put together. So we ended up partnering with Hasbro to try to learn manufacturing from them. And sometimes the best way to learn is by doing. So we ended up building about 100,000 of this robot baby doll. And she was totally freaky looking. It wasn't even a face a mother or father could love, but under the hood, there's some really cool technology, from a fully articulated audio animatronic face and capacitive sensors and all this. And we made just about every mistake in the book, but we also survived and learned a lot. So when it came time to scale the Roomba, Colin, the CEO, tapped me and pretty much gave me the prototype, put me on a plane and sent me over to China. It was like, hey, good luck, Scott, figure it out. So I definitely landed in the deep end and tried to figure out how to swim based on what I'd learned from Hasbro. And we did get to the point where we could build about 40,000 Roombas a week. And I think on my watch, we built about 4 million Roombas. So a lot of really good learnings. When you're building 40,000 a week, the last thing you ever want to do is touch the robots. So if you have like an oops and have to shave off a corner or something, like it's not really practical to file 40,000 robots if they don't fit. It is doable, and we've gone through that, but it's much better to avoid that. So hopefully today I can share with you some techniques to set you up for success. I had 10 great years at iRobot, worked up to the VP of Asia Pacific and came back as the VP of Engineering to run a team of 75 people. After 10 years there, I started Dragon Innovation, which was my last company, with the goal of helping other companies navigate that prototype to production. And we were thrilled to work with some amazing companies like Ring, Dropcam, MakerBot, Formlabs, Firo, Bose, Starbucks, and so on. So I spent 10 years there. In parallel, we started a VC fund called Bolt, really focused on early stage hardware companies. And in the course of our journey at Dragon, we raised some venture money ourselves and were acquired by Avnet, which is an amazing electronic component distributor. So got to really see that entrepreneurial journey the firsthand. Recently finished up at Dragon Innovation and started Dragon Ventures with the goal of doing a little bit of angel investing, but mostly advising hardware companies and consulting with them to help them understand how to set themselves up for success and navigate the journey that we can jump into now. So a little background on myself, I'll jump into some reasons why manufacturing can be challenging. And what I'll show next is a video from 2005. So this is before cell phones, which is crazy because it wasn't that long ago. But it's basically me with one of those little Canon cameras running down the Roomba line in China. And it'll give you a firsthand look at what manufacturing is all about. So here, what you'll see is about 1,200 workers, a lot of conveyor belts, fairly simple assembly operations involving soldering, automatic screwdrivers, arbor presses, some basic computers, motor burn-in sections, which is what's happening here, test fixtures, and so on. And this was basically just one of 4 identical rooms to support the 40,000 Roombas a week. So imagine 3 other rooms that look like this. And this is just the final assembly and test. It doesn't include any of the molding or painting or PCBAs, which is a circuit board, or any of that. So if we think about some of the reasons it's challenging, imagine, and we can walk through this on the next slide, you're, in this case, Elliot Mack, who designed the original Roomba, and you're an MIT educated product designer, you're pretty good at robotics, maybe you've read about plastics, and you basically sit in your cubby and you design stuff all by yourself. So it's not, it's not too hard. You don't need to coordinate with a lot of people. But then you ship up, after you've done the design, you ship up your database or your mechanical CAD and send it over to this factory, which is halfway around the world. And they've never met Elliot. They've never seen an autonomous floor cleaning robot, and nobody had at that time. They really have no idea what you're doing. And I'm sure Elliot's parts, despite the best of his efforts, were probably not perfect just because he hasn't designed a lot of plastic at that time. Right now, he's obviously very good at it, but he was on the learning curve there. So they get this database and they try to unpack it. And the first thing that happens is it goes to the tooling shop, where they will create the tools, which are down here, that are going to actually form the plastic housings for the robot. So these are really large, massive chunks of steel that are very hard to change later, although it is possible. So they'll go and mold the parts, and then it will go to the assembly floor that you saw, and then hopefully ultimately end up in a warehouse and make its way to the customer. Where it gets challenging is just thinking about the flow of information. So again, as a one-man team, it's not too hard, But then when you take this and spread it all the way around the world with a different time zone, different culture, a different level of education, building something that's never been built before for 5,000 people, then things get really tricky, especially if you have to make changes. So imagine that you've designed a part and it doesn't work as it should. How do you ripple that change to all of those people and keep track of what parts are already molded and which ones aren't molded? And then when you ship the robot, how do you know exactly what parts were included there? So very, very quickly, it scales to become an incredibly challenging project. The other thing is, how do you capture all of the information that those workers have learned putting together countless Roombas and then get that back to Elliot so that he can improve the design and make it more efficient? So those are some things we'll talk about a little bit more. As a sailor, I always try to include a slide with the ocean on it. So similar to the ocean that's always evolving, so is manufacturing. There's always new technologies coming out, whether it's things like laser welding or I've got some cool e-ink over here from a awesome company called Remarkable, to whatever it is. Like it's there's always new stuff coming out. Generally, there's manufacturing popping up in all sorts of new locations. One of the things I'm excited about with COVID is that it's driven, I think, a lot more motivation to build in the US, which I think is fantastic, because it's a lot easier to build with a factory that you can just drive to, that has no time zone difference, no language barrier, and a lot tighter communication. So that's been one thing that's actually been good from COVID. But we're also seeing China expanding a lot more manufacturing in Europe and Taiwan, in Singapore and Johor, Batam, Vietnam, and so on. So there's all these new manufacturing locations, and each one is different. So you have to stay up on that. There's certainly new tariffs. I think all folks know about the significant tariff that we put on China manufacturing, which would have an impact when you consider where to build. And then for hardware companies, there's also, we always have new competitors that we have to be more efficient than to stay relevant. So again, like the ocean, it's a continually evolving landscape. It's also challenging in that there's so many unknown unknowns. We don't even know what to watch out for. And one of my goals here in working through this is that hopefully I can expose you to some of those unknowns, and then we can come up with a plan for how to manage and mitigate the risk. I won't go through all of these, but I will just pick on a few of them. I'll talk about lead times a little bit. So generally, when you're building a prototype, you'll order your electronic components, say from DigiKey. You get them the next day and you're good to go. However, when you get into higher volume, you'll find that DigiKey just gets to be too expensive. So you'll either work with the chip supplier directly or maybe a distributor like Avnet. And what you'll find is that the lead time goes from 1 day to often 6 to 8 to 12 weeks. In some cases, for multi-layer ceramic capacitors, it was even 72 weeks. So imagine you're trying to hit a certain launch date for your product. You've advertised it, but for some reason you included one of these capacitors that you can't get for almost 2 years. That can really, really have a big negative impact on your business. So it's incredibly important to understand what the lead times are and be able to stay on top of those. Another big thing that you have to keep track of is, how do you select a great factory? Do you do it nearby? Do you do it overseas? How much should you be paying them? And how do you manage them? These are all things that generally you don't need to deal with when you're building a prototype. And as we looked at, if you're building 40,000 a week, it's not too hard to build that many, but it's really hard to build that many at the right cost, on time, and the right quality. So how do you avoid mistakes so that you don't have to rework 40,000 of your products and get over your skis? Those are all things that are really important to think through. The other thing, and then we'll start to jump into some solutions, is as you go from one to many, there's a fair amount of complexity for it, or sort of built into the process. So, and I'll dive into this in a subsequent slide, but if you're just building one unit, maybe you 3D print it and you can absorb a little bit higher cost. But as you think about high volume manufacturing, then you have to convert that design from a 3D printed format to something that you can injection mold, or maybe you can make out of sheet metal. And that has a whole different set of design criteria. We touched upon the schedule a little bit. Um, for quality, again, if you can adjust it and watch the user use it, that's one thing. But when you have to send these products out to somebody's home and you never get to see how they use it really, other than a little bit of testing, the quality has to be much, much higher, not only to provide the functionality that the customers expecting, but also to make sure it's safe, to make sure that it doesn't hurt the customer, that it doesn't burn down their house, that it doesn't create any other problems. So there's a lot of complexity that's going to come with high volume. And this is just a quick little eye chart talking through some of it. I'll look at the mechanical line, but the same approach would hold for electrical and so on. So again, as we talked about for mechanical, if you're just building one, you probably 3D print it or create a hand sample. But as you start to get towards 100 units, those are going to be too expensive and they're going to just take too long. So you'll probably start thinking about maybe making a rubber mold where you can get 50 shots out of that one tool. And that's a lot more efficient from a time and cost perspective. And that's great. And then you'll be like, all right, well, why don't I scale up to 1,000 units? How am I going to do that? That's where things like injection molds, which you could do through Proto Labs, they do a great job, or creating your own tools will give you the ability to create multiple units at a much, much lower piece price. But they do require understanding injection molding to be able to do that. So again, things get more and more complex as your volume goes up. For tooling, we add complexity because we actually have to build the tool to create the part. So it's a lot more than just taking your model and then printing it. But there's that intermediate step of creating the drawings and then creating your injection molding tool, figuring out the right process parameters, so temperatures and pressures and times, to then generate your part. And this all adds complexity and risk to the process. So anyhow, just a quick overview of some of the challenges that make it hard to go from that prototype to high volume. So now let's switch gears and look at some of the tools that we can use to set you up to succeed. So the first thing you should do is create a BOM or bill of materials, and do this early and stay on top of it. Don't let it get away from you or grow too old. Now, when we think of a BOM, it's really, really important that it's complete. So think about you're building a cake or you're baking a cake. This has got to have all the ingredients required to bake that cake. If you forget something, no matter how small it might seem, it's going to prevent you from making the cake or building your product. So for example, it needs to include all of the electronic and mechanical components, but it also has to include the packaging and the poly bags that keep the parts from scuffing, and the tape and the labels. All of these things have lead times and need to be purchased and have a cost associated with them. So it's really important to itemize this in your bill of materials. These are some more details of things you might put in there. So you can read through this later, but if you do make the investment to create a bill of materials and keep it updated, it's going to enable you to do all sorts of cool things. I've listed a few of them here. And again, I won't dive into all of them, but just pick a few for an example. So one, generally people want to know what is the cost to build this product, which we call cost of goods sold, or COGS. So if you have your bill of materials and know all the parts associated with it, there is a way to assign a cost to each one of those components, and then include the labor and markup and overhead of the factory that will let you know how much you should be paying the factory for the product. So this can be really important just to make sure you have a viable business. I touched on lead times a little bit. So in your BOM, if you include lead times, that will help you understand your schedule. We'll spend a lot of time talking about cash flow at the end. Another cool thing you can do with a great BOM is use it to pick your factory and be able to run a very robust RFQ, or request for quote process, so that you can select a great long-term partner. But all of this is built on the foundation of the BOM. And it's one of these where it's easy to keep current if you start early and keep it updated. But if you get too far along, it's really painful to have to go back and try to remember what are the different parts that you had. And again, if you forget a part, it really can be devastating. Just a quick look at a bill of materials, and there's all sorts of different ways or lenses you can look at a BOM. What I've shown here is a hierarchical BOM or an indented BOM, where for a given product, in this case, it's a fictitious jetpack, what we do is break it down by the major components. So the primary component is the jetpack body. And you'll see to make up the body, we've got some screws, some nuts, some bolts, some washers, and so on. Each one of these, we can keep track of the cost, the lead time, and so on. And if we wanted to build a SKU with 2 jetpacks, then we could just double the jetpack quantity, and that will pull everything along with it. So super helpful and easy to understand that way. But if you're the factory, you may want to take a different look at the BOM. So still same data, just viewed differently. So in this case, what we've done is created a flat BOM where we get rid of the indenting and basically consolidate all the parts by component. So I've started with the electronic components. And what it's going to do is look across all of the different modules and then consolidate, in this case, the capacitors, so that you know to build this one SKU, you're going to need to order 12 of the first capacitor, the 12 I'm getting from usage. You can see the individual cost of the capacitor, the extended cost, which is just usage times the unit cost, and then the lead time, which again is incredibly important if you're trying to hit an actual schedule. So with a good BOM, you'll be able to look at it in an indented view and a flat view, and be able to slice and dice it as you need to. But the important part is getting the data in there. So that's your foundation, that's your bill of materials. Once you've got that, what I found is helpful with any complex task is to break it into much simpler parts. And for me, that's the manufacturing triangle, which is cost, quality, and schedule. And the trick here is trying to find the right balance for all of these. So if you were building a medical product, for example, you might want to have really high quality, but you're potentially a little less cost sensitive. If you're building a promotional item to hold makeup and CVS, with that, it's all about schedule. And usually they can turn those things around in 2 weeks. The quality is probably not the primary driver, and the cost isn't super important, although it is a factor. The hardest thing, I think, is building consumer electronic products, because you got to hit all 3. You have to launch on time, and generally that's for the holiday season. You've got to be at a cost so that you can make money and consumers will still buy your product, and you have to be at the right quality level. So it's sort of the Olympics of managing the triangle. And with this, you can think of trade-offs. So if you could spend as much money as you wanted, it's not too hard to launch earlier with a great quality. But again, nobody's going to buy the thing because it's too much. If you could launch it lousy quality, then it's not going to cost a lot and you can do it quick, but nobody's going to buy and keep it. And likewise on the schedule, if you could take forever, then you can get the perfect product, but it's your competitor likely is going to come in. So it's a matter of getting the right balance here. And this is a great discussion to have up front as you're just finishing up your looks like prototype, so that you can figure out, where do you want to prioritize and what are those trade-offs for each one of these. So what I'll do here is let's pick each point of the triangle and dive in a little bit. So looking at cost, I generally will separate it into 2 main buckets. The first bucket on the left here is the unit cost. And as I touched on a little bit, the cost of goods sold captures that, where it's more than just the material costs, including packaging and accessories. But you have to keep in mind that not every material that you buy is going to end up in a finished product, but there's going to be some scrap. Things just get screwed up along the way occasionally. And you do want to try to drive this down to 0.25% or 0.5% as you can. Usually when you first start a line, 3 to 5% is acceptable. But this is all real money that you have to keep track of. You also have to pay the factory workers to put together the product. So that's your labor. And then the factory has to make money, which is their profit. So that converts your bill of materials into your cost of goods sold. But there's still some other costs you have to consider. How do you get it from the factory to the end customer? That's going to be the logistics or your shipping. As a company, you probably want to make a profit. So you've got to add the amount of money you want to make on top of that. And potentially you offer a warranty where you've got to cover the cost of returns. So that'll give you the sale price of how much money you should sell the product for. And that's, again, tied to the unit itself. In the other bucket is what I think of as non-reoccurring or capital costs. And those would include things like the cost of your engineering team, the cost of the tooling. So you remember on the picture with Elliot, we had on the bottom left corner a big steel mold for injection molding. Those are going to cost, thousands, if not tens of thousands of dollars. And those are all things you have to keep track of, along with any certifications, be it UL testing or a CCC or whatever you need for whatever country you're selling it in. These are kind of one-time costs, but aren't directly tied to the volume of the unit. And I found it as a best practice to keep the two of them separate, so that you can really understand what they are. So that's the cost side. And again, we won't dive too deep, but certainly please let me know if you have any questions. On the scheduling side, again, this is a quick overview of what it takes on the top left, kind of working its way down to the bottom right to get from tooling all the way to full production. And these are standard milestones. Each one has a typical duration between them. Again, here I just want to build awareness or focus on making the unknown unknowns known unknowns so that we know what we don't know and then can come back to manage those. But this is just a quick overview of what a manufacturing schedule milestones and tasks might look like. I wouldn't be complete if I didn't talk a little bit about sustainability, which is something we think about a huge amount these days. And for me, I'd always use the analogy of an alphabet, where A is the idea goes off, let's build this product. And then Z is we finally get the product to the customer. And up until a couple of years ago, that's the way I thought about it. That was basically the life of the product. But I think a much, much better way to think about it, especially because there's so much junk in the world and landfill's a real problem, is to revise our model. So the A is still the idea, let's go build this thing. But instead of Z being customer receives a product, that's probably more in the middle of the alphabet. But then there's a whole second life of the product from when that customer decides they don't need it anymore until when the product is returned to the earth. And ideally, there's ways that it can either be repaired so that the customer can use it for longer, or it can be redeployed to a different customer, or have many, many different uses before it actually ends up in landfill. There's the old adage, reduce, reuse, recycle. Obviously, reduce is the best option, followed by reuse and recycle. We had a very linear economy prior, where it was the first example I gave. We'd make something and throw it out. I think today we're in a little bit more of a recycling economy. And again, recycling is the third option. So it's better than nothing, but it's not the end all be all. As we think about recycling, one of the key things is it's important to be able to break the product into individual recycling streams. So you want to be able to separate the circuit board from the plastic. Any sort of plastic ideally wants to be just one type of resin and not a mix. So that would mean try to avoid like overmolding or solvent bonding of two dissimilar plastics, but make it so you can separate the boards, they go in one recycling stream, separate the ABS housing, that goes in another one. And that'll give us a little bit of efficiency. But where I hope we're going is much more of a circular economy, where we can just keep reusing these products and repairing them so that they have a much less impact on our society. And if you haven't watched it yet, I would really highly recommend you watch Manufacturing Landscapes. It's an amazing movie on Amazon that will open your eyes to manufacturing, but also what happens to these products downstream. I think it's all of our responsibility as we build products to think through, what impact we're having. Definitely take a look at that. So that's my pitch for thinking a little bit more along the lines of sustainability. Going back to the manufacturing triangle, we talked about cost and schedule. On quality, I love to look at this picture because it's horrifying. This guy is having a bad day. And I always ask when I'm in front of a live audience, like, does anybody know who this is? And most folks don't, but it's the head of Toyota. I don't know if people remember, it was probably 5 or 6 years ago, Toyota had a massive recall of their cars. And I think they made clearly the right choice in doing that. But I just feel the pain on the CEO's face for the potential impact on the customers, the impact on the business, and sort of that story is you don't want to be this guy. So we want to avoid getting in this position in the first place, and that's where we think about quality. There's all sorts of different types of quality, and it'd be longer than we have together today to go through. Here's a few to think about. Most folks are going to focus on the functional side of quality. So does a product do what it's supposed to? And that's incredibly important. But keep in mind, there's a lot of other things to consider. One of the ones that I often will mention is that if you are building in high volume and have electronics in your product, there's a pretty significant statistical probability that, say, 1 out of 1,000,000 products is going to catch on fire. And you need to have a good plan in place to put that fire out and prevent that from hurting anybody or damaging any property. And there's absolutely ways you can do it from an engineering perspective. But the trick is you've got to do it up front. You can't wait until the product is already shipped, because there's no over-the-air updates for hardware, at least yet, unlike software. So these are all things you want to be really thoughtful with upfront. We also will often say in manufacturing, the early decisions cast long shadows. So this is one of those that you got to get right. So please do consider quality as equal importance, if not more importance, than cost and schedule. And again, I won't dive into these too deeply now, just because I want to make sure we leave plenty of time for questions, but there are a lot of things that can go wrong. One of the most fun tests I always find is a drop test, where you'll build your full product, and then typically in the factories, they have different types of floors. So they have linoleum, and they have concrete, and they have wood. And then on the wall is just a long yardstick. And you might say, all right, we're going to do 10 drop tests in random orientation from 36 inches, which is like the height of a table. And they'll take your beautiful product and then just drop the thing on the floor and see what happens. And ideally, it still works after 10 drop tests. If it does come apart, you don't want to have any sharp edges, or sometimes you'll design things so that they actually do become disassembled but don't break, and then the user can put it together again. But if you imagine, again, just building a prototype, as we said, it's not that hard, but building a production product where it has to withstand this brutal drop test is a whole different ball of wax, and it takes a lot more engineering to be able to do that and have confidence. The other thing to consider is environmental. So imagine you built the product, say, in China in the summer, in southern China. So it's really hot and really humid. Then you put it on a FedEx plane and you brought it up to Alaska, and they're having a cold spell. So it's really cold. How do you ensure that there's not a rainstorm within the box as all that humidity comes out? And then you fly it down to Miami and put it in the back of a truck, and it goes over an old dirt road and bounces around. How do you then make sure that it doesn't get all scuffed up? So these products really have to be quite robust to survive just the shipping product, as well as the whatever the customer might do to them. And again, that does make it a bit more complex. I think we've seen the cost of having poor quality, and it, depending on the size of your company, can go into the billions of dollars. You also can really hurt people. Again, you don't want to burn anybody's house down. So it's important to think through, how do you handle products that plug into the wall or have batteries, or basically access to any sort of large stored energy, so that you don't create any issues. good things to think about ahead of time. Towards that end, within quality, there's all sorts of different approaches to testing, from the upfront during the design to as the product is built on the line, and then after it's built, doing some additional testing. These are all things that you want to design into your approach. And again, I won't dwell on that too much. So that's a super quick overview of the manufacturing triangle: cost, quality, and schedule, which is all built on that foundation of your bill of materials, or BOM. I'll just touch very, very briefly on design for manufacture and assembly, or DFM and DFA. There's also design for quality, design for cost, design for sustainability, design for repairability. Like, you can design for just about anything, but I'll focus on manufacturing and assembly. Generally, we would start with design for assembly, which is how do we put the different parts together? How many parts do we actually need, with an eye towards reducing part count? And then once we've got that, we jump into design for manufacture, where we actually figure out how to build the part. Lots of great resources here that you can climb the learning curve on design for assembly and design for manufacturing. What I've tried to do is just simplify it into 10 main points. And we'll, again, just go through these super quick. One, as you saw with the video of the Roomba line, if something can go wrong, it absolutely will. This is one of my favorite pictures here, which is the wiring harness for a car. So it's got all of these crazy connectors, cables, wire paths, and what have you. And these typically tend to be almost all like hand built. So imagine thinking about, how do you create the work instructions for this and have confidence that when it's put together, it's put together the right way? How do you design it up front with quality in mind? And then how do you test it along the way? Because this would just be a nightmare to rework, and incredibly expensive. So as you think about, if anything can go wrong, it will. Keep this picture in mind. Number two is that things always try to go back to where they started. So a simple example here of just bending a piece of metal. I think for all of us, we know after you bend it, it does rebound a little bit. And thinking about how do you design your test fixtures to accommodate that that spring action of a part. You could also think about it from an injection molding standpoint, where after you shoot a part, they tend to shrink a little bit. Usually ABS shrinks about 0.5%. So how do you accommodate that in the tooling? But again, things are just more complicated than they might seem on the surface. If possible, for number three, try to stay 2.5D. It keeps things simpler. Although I will say, thanks to Apple, which I think has been awesome from a design standpoint, there are a lot more really cool organic surfaces and things like that, which today with better tools we can handle. But in general, if you can just do something 2.5D, and there's not an aesthetic reason or functional reason to make it more complex, then just try to do that. It will make your life a lot easier. Here's an example of CNCing. And for folks that have CNC'd, as you know, with just a square end mill, it's pretty easy to clean off a face or an edge. But if you have a surface and you have to put in a ball end mill, and there's just a lot more time to do those tool paths and get an aesthetically pleasing surface. So again, try to pick your battles. Weird things happen when you go from liquid to solid. So again, this is really talking about injection molding. Which is a deep topic we can go into, but you get sink marks, which are shown by the arrows here. You may get weld lines or knit lines. You get shrinkage and warping. So thinking through your part design to make it as simple to injection mold as possible. And again, it's a trade-off between aesthetics, tooling cost, materials you pick, cost, schedule, and things like that. But it's all good things to be thoughtful about. More times you handle a product, the more defects that get introduced. Pretty self-explanatory. Vibration is your enemy. So being a roboticist, the bane of all robots is cables and connectors. Generally, you'd want to have some sort of a strain relief and lock on a cable just to make sure that as it is on the back of that truck going down the dirt road, that the cables don't get loose, because that can cause a return and have a significant impact on quality, if not safety. So be careful and generally pick good connectors. It's a good investment. Fewer parts is better. And that's one of the basic tenets for design for assembly. If you have fewer parts, you don't need to remember to order them. You don't need to pay for them. They don't have lead times. They take less effort to put together, less opportunity to introduce error into the system. So what I've got here is just a simple diagram of let's call it a throttle plate for a carburetor, where the original design is on top with a bunch of parts, and then it was able to be redesigned with more of an eye towards design for assembly down to 2 parts with some sort of a press fit between the 2 of them. So the bottom is a much better design. Number 8, sharp corners are rough. Again, whether you're stamping, forming, or injection molding, they're just a lot tougher to do, and it's easy to visualize the example that we show on the bottom here. 9, you've got to control your processes so that you understand them. If we're injection molding a part, it's going to shrink. So we want to be able to measure how much does it shrink, what are the internal stresses on the part, and have confidence that it's going to perform as we need it to. And then finally, just wrapping up, you have to know when to break the rules. These are things when you do break them, you should have a good reason why you're breaking them and not do it willy-nilly. But with all things, the intent here is just to provide a general guideline. And then you certainly will at times need to modify your approach to be able to get the product that you want out. So that's a super quick fly through of design from manufacturing and assembly. I know I've given a course, which I think took about 8 hours to dive into it deeper. So there's a lot of material there that I've just tried to compress into just a few minutes. So I apologize for that. Let me finish up with cash flow. And as I mentioned in the beginning, this is what kills companies. They run out of money. So what I can do here is let me just run a simple example, and I'll give you a quick walkthrough of what you're looking at here. So in terms of the axes, time is on the x-axis from left to right, and then money is on the y-axis. And what I've done is shown through the red bars going down all of the checks you have to pay in the process of launching a product. So you have to pay for some tooling up front, maybe you have to pay for some of your components up front. So that's the red bars. The green bars are the revenue you generate from selling your product. And then the gray is the cumulative diff between the 2 of them. So visually, you can see every time you have a red bar, it's going to knock the gray bar down a bit. And then ultimately the revenue will come in and that will start lifting up the gray bar to get in the positive region. So a few quick observations I can ascertain by looking at this diagram is, one, that this product is going to generate a positive profit because the gray is above the black line on the right. And then 2, I can understand my working capital requirement by looking at the nadir, or the bottom point of that gray shaded shape, which effectively tells me how much capital I need. So I'll just run through a few quick slides to show you the impact of negotiating better payment terms without having to change your product at all. But if you could negotiate these, it'll give you a much better chance of success. So initially, on the first 2 blocks on the left there are the payment terms with the factory, which says that effectively you have to pay the factory when you take delivery of the goods. If you were to get that so that you had to pay the factory only after 30 days post receiving the goods, that would significantly reduce the amount of time your capital is deployed. So generally you want to move the gray as much as you can above the black line as your strategy. So here you can just see there's a lot less gray. So you're going in the right direction. And that's just by getting better payment terms with the factory. The next thing is if you can get better payment terms from your customers. So what I've modeled here is that the customer would pay you 30 days after they receive the product. But on the next slide, you can see what happens is if the customer pays you when they receive the product. And this is basically moving those green revenue bars to the left, offsetting some of the expenses. So our working capital requirements went from about 200,000 to 123,000. The third knob I'll twiddle is just the sea shipping. So instead of sea shipping, if it all costs the same, if we could airship, we could go from 5 weeks to 2 weeks before we get our revenue. And you'll see as I flip the side, the green bar is moving to the left. So if I could do this, it takes my working capital requirements from 123K down to a little under 100,000. So I've been able to, by negotiating better terms and understanding my cash flow, convert from scenario 1 to scenario 5. And again, I haven't had to change the design at all, but I've been able to reduce the amount of capital I need to deploy or raise by about 150K. So that's a pretty significant amount. So as you're working through your path from prototype to production, do keep in mind the bill of materials and manufacturing triangle, but also think a lot about the cash flow just to set yourself up for success when you can make some of these choices up front that are going to cast a long shadow. And with that, I'll wrap up the presentation. I know we've covered a phenomenal amount of material super quick, but hopefully I've helped make some of those unknown unknowns, at least things that you now know you don't know and can go and manage. And if there's any questions, I'd be honored to take them.
Holy cow, Scott. I should have scheduled you for 2 hours. That was amazing. I honestly got a little shell shock from my manufacturing days with the quality statistics. I'm glad you didn't dive too deep into there. But I have a few for you as well as a couple in the chat. I'll do the ones in the chat first. Thomas asks, since hardware is hard, what if you could assemble or link together established hardware and standards to create an entire new category in a given industry like Internet of Things? Is not assembling components together, hardware and software, easier to scale than trying to create or build something original or from scratch?
Yes. Yeah. So I think there's been a lot of initiatives to try to standardize, as Thomas was saying, IoT. The challenge is that many of the use cases are very specific, and it's a balance between ultimate customization versus a set of standards. So for example, if you were doing a particular type of IoT device to measure some signal and report it back, you'd want to consider, is it medical or not medical? Is it need to live outside and survive the elements versus live inside? Is it cost sensitive? What sort of volume does it have? And if you were to create one universal device that would do all of that, it would probably be too expensive for anybody. So generally in those things, the hardware tends to be very, very customized. There are a few companies that have tried to standardize it. Avnet, the company I used to work for that acquired Dragon, has a really nice offering around IoT where they can provide the sensors, the processors. They work with Microsoft on Azure for the cloud, and then they've got a whole team of developers to help with the software. And there's a bunch of other competitors out there that are trying to do that. But I think ultimately these things tend to be so customized, it is hard to find like a off-the-shelf universal solution.
And if I can add to that, I mean, dealing with existing infrastructure is going to be the most difficult portion, but it's also the easiest and most cost efficient. I mean, for example, certain Internet of Things, for example, the electronic locks for front doors, they're finding that it's easier to add on something to an existing door hardware, or adding on to a, for example, stove, adding on a knob to an existing stove than selling or creating a new stove, or having a consumer have to purchase a new stove. So you can create existing infrastructure to be more advanced and really go along with the current trends, I should say. But I would say it's more cost efficient for both the producing company as well as for the consumer.
Yes. Yep.
The next question is from Aaron. He's asking about your Dragon Ventures switch from Dragon Innovation. He's asking if you have a new website, and I think he joined just after you and I were talking about that. I'll let you answer the question, but I know you're working on it.
Oh, sure. Yes. Yeah. I just made the switch. I think October 15th was my last day at Dragon Innovation. So I'm working on the website now, learning Wix, and working with my ID designer. But yeah, hopefully in the next couple of days, we'll have a Dragon Ventures website up.
Aaron, I'll connect you as well. What other questions do you have for Scott?
Hey, Mike, I have one. This is Jake Miller.
Go ahead, Jake.
Hey, question for you, Scott. If you had like side by side the ability to use a Chinese manufacturer or South Korean manufacturer, given and everything else is the same, given everything that's happening with China right now, could you speak to the political difference right now and the danger for companies that may source from one country versus another?
Yeah. So I think a lot of it comes down to the relationship you have with the factory, maybe even more so than where they're located. I think with any business, everything is personal, and certainly within China, we're saddled right now with a pretty significant tariff, and it's hard to know how the relationship will develop in the coming months, depending on the new administration. But I would always take a factory that I understand and trust versus one that I don't. And I would prioritize that over where they're located. My kind of top filter is work with people local if you can. But if you have exhausted that and there's just nobody local that meets your criteria, maybe they're too expensive or don't have the scale, then the next thing is look, outside, be it Mexico, China, Vietnam, South Korea. But the trust is so critical to make sure that they're not going to steal your IP, that they're going to prioritize providing a great product to you on cost, on schedule, on quality, even more so than where they're based. The different countries all have their own unique attributes. So China has just phenomenal infrastructure, domain knowledge, a reasonable labor rate. They're about $4 or $5 an hour, but you do offset that with the tariff. If you go to places, say like if we go over to India, the labor rate is much lower. So it's great for less technical goods like garments, where you don't need to have that domain expertise and you don't want to pay for it. Taiwan has been doing a lot of great work, I think, especially with the pressure that's being put on China, that a lot of their CMs have really taken off. But yeah, for me, it's always, I got to work with a partner I trust. And ideally, I would have feet on the ground in the factory. If it's a local, it's my own feet. If it's overseas, then they're either part of my company over there, or that was kind of our value prop with Dragon, that we, out of our team of 25 people, we can instill dragons in the factory. So you had eyes and ears and expertise where you needed it.
Great question, Jake. I'm really glad you mentioned the triangle too, because obviously, typically you can only choose two of those things, right? Like you can get it fast and cheap, but then you lack quality. Or if you want quality, then you usually get it slower. But oftentimes the resolution to getting that third piece of the triangle is through continuous improvement and lean Six Sigma projects. And a lot of times I know it's becoming more popular that the purchasing business is actually doing projects at their suppliers, at the supplier level, to actually, it's mutually beneficial that they can do a project for another company, but they're receiving that return. So it is possible to get all three sides. It just takes a little bit extra work. My question's around sustainability. I've had a couple of roles with Pepsi as well as GE, where I initiated zero landfill projects. I actually started the GE Appliances zero landfill initiative at the whole park. And my issue with sustainability came in, use Apple. Apple, sacrifices, they are more focused on profitability versus obsolescence, right? Like they come out with a new phone at least once a year. They get rid of plugins and make you buy something extra, or different add-ons that are completely obsolete from the last. My thought is that did your A to Z, and you made the end of life the end versus delivery to the consumer. Where do you see the future of customer receiving to end of life? I know my biggest issue has been from the scale of logistics and the unassembly process. And if companies like Apple continue to make components obsolete, then the supplier level is also going to be making products obsolete to keep up with profitability. So how do you see that section of the N through Z improving over time? What's going to be changing?
Yeah, so I think it can happen a few ways, and I'll also be the first to admit I'm climbing the learning curve here too, and welcome the discussion so we can all get better. But one is driven by the product company, so making the conscious choice not to do overmolding or allowing the product to be repairable. All of these things require more engineering and more cost and more time and more quality tests. So there is a very real cost to it, as opposed to taking the easy way out. But hopefully, as the consumers get more and more educated, they will prioritize paying a little bit more for a product that's more gentle on the earth. At Dragon, we were working with one great company that I think still in stealth mode, so I won't say too much about them, out of New York. But their whole premise was to be able to make the product the last one of that type that you owned, so that when motors did break, you could drop in a new replacement. But again, it did come at a cost in terms of price, or for modules, you often need a double wall thickness or additional costs from connectors and things like that. So that's one bucket. The other bucket would be on the government regulation side. So trying to mandate that there is some sort of ability to recycle or reuse the product, and potentially providing incentives on that. I'm by no means an expert in that, and I know it can be a sticky wicket, but that is another way to potentially provide a corrective force to do that. Because my heart just breaks when we look at these landfills, or I do a lot of sailing, and you're 1,000 miles offshore and see plastic floating by. It just kills me. So I think we've got to do it. And for me, I've built, I think at this point, maybe hundreds of millions of product, and I'm sort of having a rethink. Is like, oh, that's a lot of landfill that I've helped contribute. So how can we be smarter? People still are going to want to create new businesses and make money and help people. But I think there is ways that for a small sacrifice, we can do better than we have.
Yeah, unfortunately, I think, with cancel culture becoming a new thing, I don't even think cancel culture is strong enough to deter Apple from that next iPhone in less than a year, or the new extras they add on. I think it's going to have to be some sort of innovation in that logistics side from the unassembly angle. But I'm not sure either, Scott. It's a difficult one, but I loved the wall that you showcased of the Roomba electronic components portion. When I worked for Continental Automotive, we did a visit to GM, and they have the same thing for cars. And to see an entire car's electronics on a wall, it was like a library. I was going through the stacks of different cars, seeing everything from windshields on the wall and the radio and the airbag modules. If you ever have a chance to go see something like that, audience, it's a really cool experience. But we are. I'll ask for any last questions. Is there anyone else that has any kind of last minute question?
Hey, Scott, is there a way we can get in touch with you after this? I have a couple follow-ups from.
Yeah, absolutely.
I can as well.
So two ways. Probably the easiest is my email, which is Scott with 2 T's at dragonventures.org, org. And I think I can just bring the slide up here that will have that. And then the other one is LinkedIn. I'm a little behind in my LinkedIn messages, but that I do get to them eventually. Probably the easiest though is email. And oh shoot, I got to do better. I didn't put my email on that. But yes, Scott with 2 T's at dragonventures.org.
I'll connect you, Jake. I'm going to hit stop on the
Great, thanks.
recording.